So for the setup of these sampling distributions of proportions, with any sampling distribution, we'll have some sample size attached to it. And with the sampling distribution of means, we were collecting averages, but now what we're doing is collecting proportions. Or you can think of those as we're collecting these percentages of a sample that represent something that we're looking for. So with these sampling distributions of proportions, we want to end up with the bell-shaped curve, because then we can calculate all sorts of probabilities and things. So in this curve, we're mapping all of these different sample proportions that could come through from some sample size n that we're taking. So to understand the center and spread here, the center of the distribution, it's like the average of sample proportions, that's just going to be equal to our population proportion. The idea being that what we expect for the population is going to be what we expect for our samples in terms of behavior. So with that, we just copy our population proportion. Then for our standard deviation of sample proportions, what we'll need to do is a calculation with a big square root. And in the numerator, we multiply P, which is our population proportion, with Q, which, as a reminder, Q is just 1 minus our population proportion. They're just complements of each other. And then we divide by our sample size. And when we do this calculation, make sure all of that is under our square root. A very common mistake is to leave sample size outside of the square root, but it should all be in there. So with that, when we're trying to map these possible sample proportions, we'll have a normal distribution given that we pass our conditions that we're going to talk about down here. And then the center of the distribution will be our population proportion. Standard deviation will be this population proportion times its opposite over our sample size. Now the conditions we need to pass in order to make sure we have a bell-shaped curve is very similar to what we saw with sampling distributions of means. We should have independence, we should have a random sample, and then for sample size we check this success-failure condition. For the success-failure condition, we're going to take our sample size times our population proportion. That should be at least 10. Also, we should take our sample size times the opposite of our population proportion. That should also be at least 10. And this will guarantee that we have a large enough sample size that we get to work with this bell-shaped curve. So let's look at an example for how to work with these kind of distributions. So here we have a survey from college students, and they were asked about their satisfaction with the online shopping experience. And what they say is they received information that 60% of all college students, that phrase there, linking to all college students, that's describing a population proportion. So the idea being, if we took a sample, we'd expect 60% to come through, but as we've seen with taking samples, there's always going to be a little bit of variability. Then they take a random sample of 2,500 college students. So that's going to be our sample size that we're looking at here. So is it reasonable to use a normal model? Now, whenever we ask about, can we use a bell-shaped curve? Can we use a normal model? That's all about checking conditions. So what we want to do is check, do we have independence? Which, if we think about responses to the survey, with these random 2,500 college students, their answers aren't going to influence each other in any way. However, one response is completely independent of the other. You can also think about the 10% condition. 2,500 college students is probably less than 10% of all college students nationwide, so we'd be good there. For randomization, making sure we have a random sample, this time they actually told us it is a random sample, so we know for certain we have randomization. Then our last piece is the success-failure, and that's where we need to do a little math to make sure we have a large enough sample size. So we're taking our sample size times our population proportion. Then we also want to take our sample size times 1 minus that value, which would be a 0.4. So that first one's going to give us 1,500. The next one's going to give 1,000. And we just want to make sure that both of those numbers are more than or equal to 10, which we definitely have a large enough sample size in this case here. If the success-failure condition fails for one or both, then we can't move forward because we don't know if we have a bell-shaped curve or not. All right, so defining our distribution, finding our parameters. So looking for our mean of the sample proportions and standard deviation for these sample proportions. For the mean, we just copy down that population proportion. So that's going to be 0.6. For standard deviation, we need to do a little bit of calculating. So we take the square root, we'll have 0.6 times that 0.4 over our sample size of 2,500. So plugging that into the calculator, that should give us a 0.0098. So now we have this center and spread for distribution in terms of talking to 2,500 college students at random and collecting this proportion of how many were satisfied with their online shopping experience. Now, if we think about a number line here, what can be kind of confusing in this section is how the number line appears. So we have 0.6, and then we can move up and down by our standard deviations. In this section, with sampling distributions of proportions, it's like the number line's representing percentages. And it's kind of like, in this case, percent of 2,500 college students. So with that, it's a sample proportion, so we have this proportion attached to our sample size. So when we work with these values, it's all in terms of percentages. So when we go to probability, and we'll talk about this when we start making our sentence for our conclusion, you're going to see these two percentages coming through in these questions. There's percentage relating to probability, which is happening under the curve. So our percentages in here under the curve that are representing like percent chance and probability. But then there's also this percent of our sample size, which is representing our sample proportions. So we're going to see two percentages coming through, but they operate very differently. So let's look at this probability question. What's the probability that the sample proportion who agree is at least 57%? So if we have our curve, what we're doing here, where we're centered at 0.6, is we're going to 0.57. So we're over here. And we want the probability of at least 57%. So with that, we're finding this area to the right. So what we'll do first is find our z-score. So take 0.57 minus our mean of 0.6 and divide by our standard deviation of 0.0098, which is going to be a negative 3.06. So we want to find this probability of being more than or equal to that negative 3.06. So we'll go to our table. Since it's an area to the right, we'll do 1 minus. And then that area for negative 3.06 should be a 0.0011. So this probability area is a 0.9989. So this is where we're going to start making our sentence. And again, what we just found here is this kind of percent chance. It's relating to a probability. Then we're going to talk about this at least 57%, but then we could relate that to our sample size and this proportion that we're trying to see. So what we could say here is there is a 99.89% chance that at least 57% of the 2,500 students agree. And that would be our solution there. So when making these sentences, be sure to separate that probability from this sample proportion. All right, let's look at one more example, trying out these topics. So here we have that the germination rate is 92%. So that's printed on the packet. So that's operating as a population proportion. We have this sample size of 160 seeds. We could start thinking about, we'll be using a value for Q. So looking at 1 minus 0.92, which is a 0.08. So first thing we want to do is discuss the conditions. Do we have independence, randomization, and success failure? So in terms of seeds germinating, independent, they're not influencing each other. They're not dependent on each other. Randomization, They don't say it's a random sample of 160 seeds, but we'll assume we're okay. What we really want to check is success failure. So taking 160 times that 0.92, take that 160 times 0.08, and make sure those are larger than or equal to 10. So with that, we have 147 and a 13. So both of those are larger than or equal to 10. So now we can use our bell-shaped curve. So defining our model, our mean is just the population proportion. The standard deviation is going to be a big square root with a 0.92 times a 0.08 over our sample size of 160. And with that, our standard deviation is a 0.0214. So from there, we can talk about these, like, it's really relating to percent of 160 seeds that will germinate. And with that, they're normally distributed. We expect 92% to germinate, and then how that will spread is by the standard deviation of 0.0214. So sketching and labeling a model, we can get this picture going of a nice bell-shaped curve. In the middle, we'll have a 0.92, and then let's go ahead to standard deviations above, to standard deviations below, and then just using jumps of 0.0214, we'll have a 0.9414, a 0.9628, a 0.8986, and a 0.8772. All right, so with that, we can see these percentages that we expect to come through, meaning like if I said I got a packet of 160 seeds and let's say 93% of them germinated. So 93% of the 160 seeds is landing about there. That's completely expected. If I had a packet of seeds and say only 80% germinated, that's way out here, and that's not expected at all. So with this picture, we can get an idea of what percentages we expect to come through. So what is the probability that more than 95% of the seeds will germinate? So 95 is landing somewhere in here. So there's this 95%. And with that, we want to find the area above. So we want to find this area to the right of that 0.95. So what we'll do first is get our z-score. So 95 minus our mean over our standard deviation. And that z-score should come out to be a 1.40. And what we want to do is find the probability above that value. So we'll go to our table, and we'll need to use the complement rule since it's an area to the right. If we look up 1.40, that should be a 0.9192. So our total area is going to be a 0.0808. So with that, there is an 8.08% chance that 90 or more than 95% of the 160 seeds will germinate. All right, and then our last example here, it's asking about unusual. And if you remember from when we talked about z-score, so we just think about our number line for z-scores. If we find our z-score and it's beyond, or it could even be at 2 or beyond, or at -2 or beyond, those are considered unusual. That's where you're getting far out in the bell-shaped curve, or the probabilities are much lower. So what we want to do here is just find a z-score. Now, notice how the numbers are given here. Here they're talking about a whole number of seeds, which if I start making my z-score right here and think about, okay, 140 minus, and then I think about my mean, well, we're working with the mean of 0.92. How we have everything scaled right now is in terms of percentages out of 160. So our mean and standard deviation right now they don't line up with how 140 is being represented. So instead, what we want to do first, before we start calculating that z-score, is change that 140 into a proportion. Change it into a percentage out of 160 so that, so that it can compare to that mean and standard deviation. So, sorry about that screen. 1 second. All right, I think I fixed it, but we're so close to done. All right, out of 160, so that proportion there will be a 0.875. And so with that, when we make our z-score, that's the value we want to use. So instead of 140, we want that to represent 87.5% of 160 seeds. So we can compare that to 92% of 160 seeds over that standard deviation that we found for that scenario. So that'll give a z-score of negative 2.1028, which is landing out in that range that's considered unusual. So that would be an unusual result because it's very unlikely. So that's our sampling distribution of proportions. It's basically when we want to talk about percentages of a sample size.